It isn't a cyberattack. It isn't terrorism. It isn't a hidden weapon. It is something that has happened for billions of years, and it begins nearly 150 million kilometers away. The sun. Every sunrise makes it feel calm, predictable, permanent. But beneath that familiar glow is a star powered by nuclear fusion. Every second, it converts around 600 million tons of hydrogen into helium. That process releases an unimaginable amount of energy. Most of the time, Earth is protected. Most of the time. Because occasionally, the sun releases an enormous burst of energy, known as a solar flare, often followed by a massive cloud of charged plasma, called a coronal mass ejection, or CME. If one of those clouds happens to be aimed directly at Earth, our planet is struck by a geomagnetic storm. And the incredible part is, this isn't science fiction, it already happened. On March 13, 1989, millions of people suddenly found themselves sitting in complete darkness. Not because power plants failed, not because fuel ran out, not because someone attacked the electrical grid. The electricity simply disappeared. In less than 2 minutes, the entire Hydro-Quebec power network collapsed. Around 6 million people lost power. Elevators stopped. Traffic lights failed. Homes went dark. Businesses froze. Hospitals switched to emergency generators. For many people, it felt impossible. How could a storm on the sun switch off electricity on Earth? The answer begins nearly 8 minutes earlier. Light from the sun reaches Earth in about 8 minutes. But plasma does not. After an eruption, billions of tons of electrically charged particles race through space at extraordinary speeds. Sometimes they miss Earth completely. Sometimes they barely graze us. And sometimes they arrive almost head-on. When those particles slam into Earth's magnetic field, they don't simply create beautiful auroras. They force Earth's magnetic shield to flex, twist, and shake. That movement generates electric currents over enormous distances. Normally, those currents are harmless. But long metal structures, especially high-voltage transmission lines, act like giant antennas. They collect those currents. The electricity entering the grid isn't the electricity engineers designed for. It's an unwanted extra current flowing directly into transformers. Transformers are the heart of every electrical grid. Without them, electricity cannot move efficiently from power stations to homes and cities. During the 1989 storm, several transformers became overloaded almost simultaneously. Protective systems reacted exactly as they were designed. They shut the grid down before even greater damage could occur. The result was one of the largest space weather-related blackouts ever recorded. And yet, by historical standards, 1989 wasn't even the worst solar storm. Not even close. To understand why scientists still study that blackout today, you have to go back much further. Back to an era before satellites. Before computers. Before electrical grids even existed. Back to September 1859. A British astronomer named Richard Carrington was doing something remarkably ordinary. He was observing the sun. At the time, astronomers projected solar images onto paper to sketch sunspots by hand. Photography was still primitive. Carrington had done this countless times before. Then something extraordinary happened. 2 intensely bright flashes suddenly appeared near a cluster of sunspots. They lasted only minutes. He immediately realized he had witnessed something nobody had ever recorded before. Today, we know exactly what he saw. A white light solar flare. The first ever observed by a human being. Carrington couldn't possibly know what would happen next. 17 hours later, far faster than most solar storms, Earth was struck by one of the most powerful geomagnetic events ever documented. The skies turned red, not only near the poles, but across much of the world. Auroras appeared over Cuba, Mexico, the Caribbean, even regions where people had never seen such lights before. Some newspapers reported that people believed dawn had arrived in the middle of the night. Miners reportedly prepared for work because the sky had become bright enough to read outdoors. It looked beautiful. It wasn't. Telegraph systems, the world's most advanced communications network at the time, began behaving in bizarre ways. Operators received electric shocks. Paper caught fire from electrical sparks. Some telegraph systems continued transmitting even after being disconnected from their power supplies. The storm itself was generating enough electrical current inside the wires. Imagine trying to unplug your computer, only to discover it keeps running anyway. That is how powerful Earth's magnetic field had become. Today we call that event the Carrington event. It remains the benchmark against which every major solar storm is measured. And here's the uncomfortable truth. The world of 1859 had almost nothing that depended on electricity. No satellites, no GPS, no internet, no aircraft navigation systems, no international power grids, no cloud computing, no smartphones, no modern banking. Today, everything depends on electricity. Everything depends on satellites. Everything depends on timing signals moving invisibly through space. That means a storm equal to, or stronger than, the Carrington event would strike a civilization built almost entirely on technologies that didn't exist in 1859. No guessing, just the facts. Scientists don't spend decades studying extreme solar storms because they're rare curiosities. They study them because our dependence has changed dramatically. Every decade adds more satellites, more power lines, more communication systems, more infrastructure exposed to space weather. The sun hasn't become more dangerous. We have become more vulnerable. And that's exactly why March 1989 matters. It wasn't the biggest storm. It wasn't the strongest. It was simply the first modern reminder that space weather isn't just an astronomical event. It's an engineering problem. One capable of crossing continents in minutes. One capable of disrupting millions of lives without warning. But here's the question that keeps researchers awake. If a storm smaller than Carrington could darken an entire province, that question isn't theoretical. Scientists have already seen evidence that an even larger disaster was narrowly avoided. In July 2012, the sun unleashed one of the most powerful coronal mass ejections ever measured by modern spacecraft. Fortunately for Earth, it missed. Not by millions of kilometers, by time. The eruption crossed Earth's orbit just days after our planet had already moved past that point in space. If the timing had been slightly different, Earth could have been directly in its path. Spacecraft such as NASA's Stereo mission recorded the event in remarkable detail. The data suggested it was comparable to the most extreme historical solar storms. It was a reminder of something easy to forget. Space weather isn't a problem from the past. It is an ongoing feature of living beside an active star. The sun follows an approximately 11-year cycle. During solar minimum, its magnetic field is relatively quiet. Sunspots become scarce. Large eruptions are less common. Then activity builds. Sunspots multiply. Magnetic fields become tangled. Solar flares become more frequent. Coronal mass ejections become more likely. Eventually, the sun reaches solar maximum, the most active phase of its cycle. That doesn't mean every day brings disaster. It means the odds of major eruptions increase. The sun is not exploding. It is constantly reorganizing its magnetic field. Imagine twisting thousands of rubber bands together. Eventually, one snaps. The stored energy is released almost instantly. On the sun, those magnetic rubber bands are loops of plasma, thousands of times larger than Earth. When they reconnect, they release energy equivalent to billions of nuclear bombs. No guessing, just the facts. Most of that energy never reaches us. Space is vast. The sun ejects material in every direction. Only a small fraction is aimed at Earth. Even then, Earth's magnetic field acts like a giant shield. But shields are not walls. When a fast-moving CME strikes, Earth's magnetosphere compresses on the sunward side and stretches far behind the planet like an enormous windsock. That motion induces electric currents in the ground itself. These are called geomagnetically induced currents, or GICs. Unlike lightning, they are slow-moving. They don't jump through the air. They seep through long conductors, power lines, pipelines, railway systems, and submarine cables. To electrical equipment, those currents are something completely unexpected. Large transformers are especially vulnerable. These machines can weigh hundreds of tons. They are custom-built. Many require months, or even years, to manufacture and replace. If enough transformers fail at once, replacing them becomes a logistical challenge as much as an engineering one. This is one reason governments and utility companies closely monitor space weather forecasts. Modern electrical grids are stronger than they were in 1989. Utilities have improved procedures. Operators receive warnings. Some equipment has been upgraded to better withstand geomagnetic disturbances. But improvements do not eliminate risk. They reduce it. Because the grid itself has also become larger, more interconnected, and more dependent on precise control systems. One failure can affect another. Power networks are designed to share electricity across vast regions. Normally, that's an advantage. During a severe disturbance, it can also allow problems to spread. Imagine thousands of dominoes connected not in a straight line, but in a giant web. Removing one piece may not matter. Removing enough pieces at once can change everything. Electricity isn't the only concern. Look above your head. Hundreds of kilometers overhead, thousands of satellites circle Earth. Some provide weather forecasts. Others support television broadcasts. Many enable GPS navigation. Others connect financial networks, emergency responders, aviation, agriculture, shipping, and military communications. Most people never think about them until they stop working. A solar storm affects satellites in multiple ways. High-energy particles can damage electronics. They can interfere with onboard computers. They can create charging effects that lead to unexpected failures. The upper atmosphere also expands as it heats during geomagnetic storms. That extra drag slows low Earth orbit satellites. Their paths begin to change. Without careful corrections, they gradually lose altitude. This isn't just theory. In February 2022, after a moderate geomagnetic storm, dozens of newly launched satellites experienced increased atmospheric drag and re-entered the atmosphere before reaching their intended orbits. The event highlighted how even relatively modest space weather can have real consequences for modern spacecraft. GPS is another hidden dependency. When people think of GPS, they think about maps. But positioning is only one function. GPS satellites also provide extremely precise timing. Power grids use it. Cellular networks use it. Financial systems use it. Communication networks use it. Many systems that appear unrelated are synchronized by signals arriving from space. If those signals become degraded or interrupted, the effects can ripple far beyond navigation. Air traffic controllers rely on satellite-based systems. Ships crossing oceans depend on them. Farmers use GPS-guided equipment to plant crops with remarkable precision. Construction crews use it to survey land. Scientists use it to monitor tectonic plate movement measured in millimeters. One invisible system supports countless visible ones. Then there is radio communication. During powerful solar flares, intense X-rays reach Earth in just over 8 minutes. They ionize the upper atmosphere. Certain radio frequencies can suddenly fade or disappear. Pilots flying polar routes sometimes experience communication disruptions during major solar events. Operators shift routes or use alternative frequencies when necessary. Again, preparation matters. Awareness matters. No guessing, just the facts. Modern forecasting has become one of humanity's greatest advantages. Spacecraft continuously observe the sun. Solar observatories monitor sunspots, flares, and coronal mass ejections. Forecast centers analyze incoming data around the clock. When a significant eruption occurs, warnings are issued to governments, utilities, airlines, satellite operators, and other critical infrastructure managers. Unlike earthquakes, solar storms often provide hours, or in some cases more than a day, of advance notice. That warning window may sound short, but for engineers responsible for national infrastructure, even a few hours can make an enormous difference. Systems can be reconfigured. Sensitive equipment can be protected. Astronauts can take shelter in better shielded areas of spacecraft. Satellite operators can delay certain operations. Power companies can prepare for increased monitoring. The goal isn't to stop the storm. That's impossible. The goal is to reduce its impact. Because while humanity cannot control the sun, it can prepare for it. Yet there is one part of the story that makes researchers especially uneasy. History suggests that the biggest storms may not arrive when anyone expects them. And the evidence comes not from satellites, not from telescopes, but from trees, ice, and the chemistry of Earth's atmosphere. For most of human history, nobody kept records of solar storms. There were no satellites, no observatories, no magnetometers quietly measuring Earth's magnetic field. If an extreme event happened thousands of years ago, who would know? The answer turned out to be nature itself. Every time high-energy particles from space collide with Earth's atmosphere, they trigger tiny nuclear reactions. Those reactions create rare isotopes, including carbon-14 and beryllium-10. Normally, these isotopes are produced at a fairly steady rate, but during an exceptionally powerful burst of solar activity, their production can suddenly spike. Trees absorb carbon dioxide from the atmosphere as they grow. Each annual growth ring becomes a time capsule, preserving the chemical conditions of that year. Ice sheets do something similar. Snow falls, it compresses. Layer upon layer builds up over centuries. Tiny traces of ancient atmospheric chemistry become locked inside the ice. Scientists can drill deep cores through Greenland and Antarctica and effectively read Earth's environmental history year by year. It is like opening a library written by nature itself. And in that library, researchers found something unexpected. Around the year 774 or 775 CE, tree rings across the world recorded an enormous increase in carbon-14. The spike appeared almost simultaneously in samples from different continents. Whatever caused it had affected the entire planet. The event was so unusual that scientists are still studying its exact origin. The leading explanation is an extreme solar energetic particle event, a burst of charged particles far more intense than anything measured directly in the space age. If that interpretation is correct, it means the sun may be capable of producing events even more energetic than those observed in modern history. No guessing, just the facts. Researchers continue to debate the precise mechanism, but the evidence preserved in tree rings is real. Nature recorded something extraordinary. Whether it was the largest solar event in thousands of years, remains an active area of research. What matters is this: the historical record available to humans is very short. Modern space-age observations cover only a few decades. Reliable electrical infrastructure has existed for little more than a century. Compared with the sun's lifetime of more than 4.5 billion years, our observations are only an instant. Imagine trying to predict the climate after watching the weather for a single afternoon. That is roughly how limited our direct experience is. This is why scientists avoid absolute statements. They do not say an extreme solar storm is guaranteed next year. They also do not say it cannot happen. Instead, they study probabilities. They build models. They compare observations with historical evidence. That careful approach has transformed space weather into an international scientific effort. Organizations around the world continuously monitor the sun. Spacecraft observe it from multiple angles. Ground-based observatories measure magnetic activity. Radio telescopes monitor emissions from solar flares. Magnetometers detect subtle disturbances in Earth's magnetic field. Thousands of measurements flow into forecasting centers every day. Because when the sun changes, the entire planet is affected. Fortunately, Earth possesses a remarkable defense: its magnetic field. Generated deep inside the planet by the movement of molten iron within Earth's outer core, this invisible magnetic bubble extends tens of thousands of kilometers into space. Without it, life on Earth would face a far harsher environment. The magnetosphere deflects much of the solar wind around the planet. Instead of striking Earth's atmosphere directly, many charged particles are guided toward the poles. That is why auroras usually appear in northern and southern polar regions. The glowing curtains of green, red, and purple light are not simply beautiful displays. They are visible evidence of Earth's magnetic shield at work. Every shimmering ribbon in the night sky represents particles being redirected away from the surface. In a way, an aurora is the planet quietly protecting itself. But during powerful geomagnetic storms, the magnetosphere is pushed to its limits. Auroras spread farther south than usual. People in regions that rarely see them suddenly look up and witness skies glowing with unfamiliar colors. For many, it feels magical. For engineers monitoring electrical systems, it can also be a warning. Because the brighter the auroras become, the more active the geomagnetic storm is likely to be. History provides several striking examples. During major solar storms, auroras have been observed in places where they are almost never seen. That doesn't automatically mean catastrophic damage will occur. It simply means Earth's magnetic field is experiencing a significant disturbance. Scientists watch those disturbances carefully. Modern instruments measure changes far beyond what the human eye can detect. Every fluctuation helps improve forecasts. Every event teaches researchers something new. One lesson has become increasingly clear. Extreme space weather is not a single event. It is a chain reaction. The process begins on the sun. It travels across nearly 150 million kilometers of space. It collides with Earth's magnetic field. That interaction affects the upper atmosphere. The atmosphere changes satellite drag. Magnetic disturbances induce currents in power systems. Radio signals become disrupted. Navigation accuracy can decrease. Each step influences the next. Like gears turning inside an enormous machine. Most of the time, those gears move smoothly. Occasionally, one turns much harder than expected. That is when resilience matters. Since 1989, utility companies have installed monitoring systems capable of detecting geomagnetically induced currents in real time. Forecast centers now issue geomagnetic storm alerts using standardized scales. Satellite manufacturers incorporate shielding and fault-tolerant designs. Airlines adjust some flight operations during heightened radiation events. Astronauts aboard spacecraft receive continuous monitoring of space weather conditions. These improvements are significant, but they are not perfect. Technology evolves rapidly, so do our dependencies. Every new satellite constellation, every additional undersea communication cable, every expansion of renewable energy infrastructure, every increase in global connectivity, all of it adds new opportunities and new vulnerabilities. The challenge isn't simply building stronger technology, it's understanding that our civilization is now connected in ways previous generations could never imagine. A disturbance that begins on the surface of the sun can eventually influence systems spread across every continent. That realization has changed how governments think about national security. It has changed how engineers design infrastructure. It has changed how scientists observe the sun itself. Because one fact remains impossible to ignore. The next major solar storm is not a question of human intention. It is a consequence of living beside an active star. The only unknown is when the next truly extreme event will arrive. And when it does, how prepared will we be? Imagine waking up on what seems like an ordinary morning. Your phone still has a signal. The lights are on. Traffic moves normally. The world appears unchanged. Then, without any sound or visible warning, space weather monitoring centers detect something extraordinary. Hours earlier, astronomers observed an intense solar flare erupting from an active region near the center of the sun. Moments later, coronagraph images confirmed what scientists feared. A fast-moving coronal mass ejection was heading almost directly toward Earth. Immediately, alerts begin moving through global forecasting networks. Satellite operators receive notifications. Power grid controllers review contingency plans. Airlines examine routes that cross polar regions. Mission controllers monitor astronauts aboard spacecraft. None of these actions mean disaster is certain. They are precautionary measures. Because forecasting space weather is a science of probabilities, not certainties. The speed of a CME matters. Its density matters. Most importantly, the orientation of its magnetic field matters. If the magnetic field carried by the CME aligns in the opposite direction to Earth's own magnetic field, the interaction becomes much stronger. Scientists often describe this as two magnetic systems connecting. When that happens, more energy can enter Earth's magnetosphere. The result is a more intense geomagnetic storm. This is one of the reasons forecasting remains challenging. Even after a CME leaves the sun, researchers may not know its exact magnetic orientation until spacecraft positioned upstream of Earth measure it directly. That often provides only tens of minutes of final warning before the cloud reaches our planet. No guessing, just the facts. Forecasting has improved enormously, but uncertainty still exists. The sun is not following a schedule. It does not announce its next eruption. Scientists observe, calculate, compare models, and continuously update forecasts as new data arrives. Meanwhile, life on Earth continues. Most people never notice the invisible work taking place behind the scenes. Engineers quietly adjust electrical systems. Satellite operators place spacecraft into safer configurations when appropriate. Space agencies monitor radiation levels. These actions rarely make headlines, because, most of the time, they work exactly as intended. Preparation is often invisible. Success looks like nothing happened. That is the goal. Yet researchers also study worst-case scenarios, not because they expect them every year, but because critical infrastructure must be designed for rare events. Bridges are built to survive exceptional loads. Aircraft are designed for unlikely failures. Hospitals prepare for emergencies they hope never occur. Space weather planning follows the same philosophy. Prepare for the unlikely. Hope it never becomes necessary. One common misconception is that a major solar storm would permanently destroy all electronics. That is not supported by current scientific understanding. The effects would vary widely, depending on location, infrastructure design, equipment, and storm intensity. Some regions might experience little disruption. Others could face significant challenges. Some satellites might continue operating normally. Others could require recovery procedures. the impact would not be identical everywhere. That complexity is exactly why scientists avoid sensational predictions. Reality is more nuanced, and often more interesting. Another misconception is that Earth's atmosphere offers no protection. In reality, our atmosphere absorbs much of the harmful radiation associated with solar activity. Without both the atmosphere and the magnetic field, life on Earth's surface would face a dramatically harsher radiation environment. These natural defenses have protected our planet for billions of years. What has changed is not Earth. It is us. Our civilization increasingly depends on technologies extending into space and spanning continents. Power grids stretch thousands of kilometers. Communication networks circle the globe. Satellites form invisible links, connecting navigation, finance, weather forecasting, emergency response, television, internet services, and scientific research. The more connected we become, the more important resilience becomes. That resilience is already improving. Utilities install devices that block geomagnetically induced currents. Transformer designs continue to evolve. Forecasting models become more accurate. International cooperation has expanded dramatically. Data collected by one nation often benefits many others. Space weather ignores political borders. A geomagnetic storm affecting North America may also influence Europe. The same event may produce spectacular auroras across Scandinavia, while prompting satellite operators in Asia to monitor spacecraft performance more closely. The sun does not distinguish between countries. Its influence extends across the entire planet. This global perspective has encouraged unprecedented scientific collaboration. Solar observatories share observations. Forecast centers exchange information. Universities compare models. Engineers publish lessons learned after every significant storm. Each event becomes another opportunity to improve preparedness. Even relatively modest storms contribute valuable knowledge. Scientists ask the same questions every time. How accurate were the forecasts? Which systems experienced unexpected effects? Which protective measures worked best? Where can improvements be made? Progress happens one observation at a time, one storm at a time, one lesson at a time. No guessing, just the facts. Perhaps the greatest achievement is that today's warnings are no longer based on surprise alone. In 1859, humanity had no idea what was happening. In 1989, forecasting capabilities were limited compared with today. Now, continuous monitoring allows researchers to watch the sun every hour of every day. That constant vigilance does not eliminate risk, but it transforms uncertainty into preparation. And preparation has always been humanity's greatest advantage. Still, every generation eventually faces a reminder that nature operates on scales far beyond human control. Volcanoes, earthquakes, hurricanes, and above them all, a star nearly 1.4 million kilometers wide, quietly fusing hydrogen into helium every second. A star whose light gives life, and whose magnetic storms occasionally remind us just how connected Earth is to the rest of the solar system. The blackout of 1989 lasted hours. The scientific lessons from that night continue today. Because researchers know something simple, the next major solar storm is not prevented by ignoring it. It is met by understanding it. Understanding begins with perspective. When people hear the phrase, solar storm, it's easy to imagine an explosion racing toward Earth, like something from a disaster movie. Reality is quieter, and far more fascinating. A solar storm is not an attack. It has no intention. It is the natural consequence of an active star releasing magnetic energy that has built up over time. The sun has been doing this for billions of years, long before the first humans walked the Earth, and long before anyone understood what a magnetic field was. For almost all of that time, these eruptions passed unnoticed. Auroras danced across the skies. Charged particles swept past the planet. Earth's magnetic field absorbed the impact. Life continued. Only in the last century has humanity built a civilization where invisible systems connect nearly every aspect of daily life. Electricity, communications, navigation, weather forecasting, emergency response, banking, scientific research. Every one of these systems depends, in some way, on technologies that can be influenced by conditions in space. That is why space weather has become its own scientific discipline. Not because the sun has changed, but because civilization has. No guessing, just the facts. Today, Hundreds of scientists monitor the sun around the clock. Spacecraft continuously observe its surface. Ground-based observatories track sunspots and magnetic activity. Forecast centers analyze incoming data and issue alerts when significant events occur. Engineers work to make power grids more resilient. Satellite designers improve shielding and fault tolerance. Utility operators develop procedures to reduce the effects of geomagnetically induced currents. Every major solar storm teaches another lesson. Every lesson strengthens future preparation. This is how science progresses, not through certainty, but through observation, testing, correction, and continuous improvement. That process has already transformed our understanding of the sun. Astronomers now know that solar flares occur when magnetic energy is suddenly released. They understand that coronal mass ejections can carry billions of tons of plasma into interplanetary space. They know that only a fraction of those eruptions are directed toward Earth. They know Earth's magnetic field absorbs much of the impact. They know forecasting continues to improve every year. And they know there are still unanswered questions. Exactly how often do Carrington-class events occur? Can storms larger than those recorded in modern history happen again? How will increasingly complex electrical systems respond to future extremes? Researchers continue searching for answers. Because every new observation adds another piece to the puzzle. The March 1989 blackout remains one of the clearest demonstrations that space weather can have real consequences on the ground. It showed that a disturbance beginning on the sun could influence infrastructure thousands of kilometers away. It reminded engineers that electrical grids exist within a much larger natural system. The event became a turning point. Utilities reviewed their procedures. Scientists expanded monitoring programs. Governments recognized space weather as a national infrastructure concern. International cooperation increased. One storm reshaped decades of planning. Then came July 2012. A powerful coronal mass ejection crossed Earth's orbital path, after our planet had already moved on. The near miss reinforced another lesson. Timing matters. Sometimes, the difference between a direct impact and no impact at all is measured in days. The universe often works on margins far smaller than human intuition expects. That realization is both humbling and inspiring. Humbling because it reminds us that Earth travels through an active cosmic environment. Inspiring because humanity now possesses the tools to observe that environment with extraordinary precision. Every image returned by solar observatories, every measurement from satellites, every improvement in forecasting, every upgrade to critical infrastructure, all represent the same idea. Knowledge is our first line of defense. No guessing, just the facts. Perhaps that is the true legacy of the 1989 blackout. Not fear, preparation, not panic, understanding. The blackout did not prove civilization is fragile. It proved that hidden vulnerabilities can be identified, studied, and reduced. That is exactly what scientists and engineers have spent the decades since 1989 doing. The work continues, every single day, because the sun never truly sleeps. Its magnetic fields continue to twist and evolve. Sunspots appear and disappear. Solar flares continue to erupt. Coronal mass ejections continue to stream into space. Most never affect Earth. Some create beautiful auroras. A few become valuable scientific case studies. And somewhere in the future, another significant solar storm will almost certainly occur. No calendar can predict the exact date. No model can guarantee its strength. But whenever it happens, humanity will face it with far more knowledge than it possessed in 1859. Far more preparation than it had in 1989. And far more understanding than ever before. The next great solar storm will not simply test our technology. It will test how well we have learned from history. From Richard Carrington watching the sun through a telescope in 1859, to millions of people sitting in darkness during the Quebec blackout of 1989, to modern spacecraft that watch our star every hour of every day. The story has never really been about destruction. It has been about discovery, about recognizing that Earth is not isolated. It is part of a dynamic solar system, connected to its parent star by invisible magnetic forces, stretching across nearly 150 million kilometers of space. Every sunrise is a reminder of that connection. Every aurora is evidence of it. Every scientific mission brings us closer to understanding it. The sun gives Earth warmth. It gives Earth light. It made life possible. Occasionally, it also reminds us of its extraordinary power. And perhaps the most remarkable fact of all, Is that a civilization capable of being affected by a solar storm is also a civilization capable of predicting it, preparing for it, and learning from it. That is the difference between fear and science, between speculation and evidence, between guessing and the facts.